Acids and bases, high level 6, pH curves. Essential idea. pH curves can be investigated experimentally, but are mathematically determined by the dissociation constants of the acid and base. An indicator with an appropriate endpoint can be used to determine the equivalence point of the reaction. Nature of science. Increased power of instrumentation and advances in available techniques. Development in pH meter technology has allowed for more reliable and ready measurement of pH. Let's review acid-base titrations. So an acid and a base will give us salt and water. So it's a neutralization reaction. But what does this really mean? Does the product have to be neutral? But what if it was a strong acid and a weak base? It wouldn't be, would it? So it's not always neutral. Do the moles of acid equal the moles of base? Well, that very much depends on the type of acid and the type of base. You might have sulfuric acid, which has 2 hydrogens available, and sodium hydroxide, which only has 1 hydroxide ion. Moles of H plus equals moles of hydroxide ions. Yes, indeed. These do need to be even for a neutralization reaction. They need to cancel each other out to make water. Otherwise, you'd just have excessive hydrogen ions, so it'd still be acidic, or you'd have excessive hydroxide ions, so it would be basic. Let's consider the equations for 2 neutralization reactions below. You've got strong acid and strong base, hydrochloric acid and sodium hydroxide, giving us sodium chloride. And you can see here, 1 hydrogen ion reacting with 1 hydroxide ion to give us water. So it's neutralized. Here, you've got 1 mole of sulfuric acid reacting with 2 moles of base. But the reality is, of course, you've got 2 moles of the hydrogen ion from sulfuric acid reacting with 2 hydroxide ions to give us 2 moles of water. So a neutralization reaction is cancelling out those hydrogen ions and hydroxide ions to give water. And you get, if it is a strong acid and strong base, you would get a neutral solution with equal moles of hydrogen, equal moles of hydroxide ions. If you remember from practicals last year, we used the term equivalence point and end point. Let's review this. If we consider an acid-base titration where a base of a known concentration is added to a known volume of an acid with an unknown concentration, we have the titrant with sodium hydroxide, and we've got hydrochloric acid as an analyte. The equivalence point is where the number of moles of hydroxide ions added equals the number of moles of hydrogen ions in the acid sample. Or you could say the number of moles of hydrogen ions added would equal the number of moles of hydroxide ion in the base sample if it was switched around. So equivalence point is when you have equivalent amount of hydroxide ions and hydrogen ions. The end point is just the point at which the indicator just changes colour. It happens immediately after the equivalence point. And we can assume that the end point equals the equivalence point if you're using the right indicator. Titration curves. These are graphical analysis of neutralization reactions. A titration curve, or pH curve, measures the change in pH of the analyte versus volume of titrant added. In this case, the analyte would be the acid, because you can see we start off with a low pH, and we're adding base. The titrant is the base, and as you add more base, the pH increases, it gets more and more basic. The titration curve shows changes in pH of the solution over the course of the neutralization reaction. These changes give useful information about the type of acids and bases used in the reaction and about quantities needed for neutralization and half neutralization. So pH is on the left, on the y-axis, and volume of titrant is on the x-axis. The general features of a titration curve. You've got the section below here, which is when the initial addition of titration produces a little gradual change in pH depending on the strength of the acid. So in this case, you're adding a base to an acid, and you can see it doesn't change too rapidly. Then all of a sudden you get a sharp pH increase near the equivalence point. The pH at the equivalence point indicates the type of salt it forms. In this case, the midpoint of the equivalence point is the midpoint of the sharp vertical section. The volume of base added at this point is the volume needed to neutralize the acid. In this case, 50 milliliters. And you continue to add base, tighten, it simply maintains the pH of the base eventually. Let's look at an example. We've got a strong acid and a strong base. Let's say it's hydrochloric acid and sodium hydroxide to give us the salt, sodium chloride and water. Initially, we've got a low pH, which suggests a strong acid. It has a pH of 1, it's a strong acid. You've got the flat section as you initially add the base. Then you've got the tall, steep vertical increase. You can see that the equivalence point is at pH 7. So we know that a neutral salt is formed because the parent acid is a strong acid and the parent base is a strong base. And finally, we see you can get a high final pH, which suggests a strong base. It confirms we had a strong base. You've got a pH of 12. No, the last one wasn't finally. There's a number 6. The volume of base needed to reach the equivalent point is 50 milliliters. So you can look at the tall, steep vertical increase, follow that down to show you the volume of base needed to reach the equivalence point. What if we had a weak acid and a strong base? Ethanoic acid and sodium hydroxide. Well, the initial pH suggests a weak acid. It's got a pH of about 3. Then you get the strange shoulder section, which we'll talk about later, because you're getting a region which is buffering. Then you get the steep vertical increase, but you'll notice it's a far shorter section than when we had strong acid and strong base. The equivalence point is not at pH 7. It's above 7. So we know that a basic salt is formed. The parent acid is weak and the parent base is strong. The volume of base needed to reach the equivalence point is 50 milliliters. And here it's worth looking at the half equivalence point, which is just the pH at half equivalence point is the pKa, and that's why it's important to know. And you can see that the equivalence point is 50 ml, so the half equivalence point is going to be 25, just half it. You take it up, you can go along your graph, and you can find what the pH is at pKa. Oh, sorry, you can find the pH at a half equivalence point. This will be the pKa. Oh, oops. 1 second. All right. Finally, you've got a high pH, which suggests a strong base. So you can see this graph tells us a whole bunch of information. Weak acid and strong base, again, this time let's talk a little about that shoulder section upon initial addition. It's the buffer region. Adding a strong base to a weak acid forms a buffer, if you remember the last presentation, up to a point. Say if we had ethanoic acid and sodium hydroxide to give us the sodium ethanoate, we're going to get a point in time when you've got the ethanoic acid and you've got a whole bunch of the anion in solution at the same time. That means this can mop up hydroxides, this can mop up hydrogen ions. So it's going to be buffering for a little bit. Like I just said, if you want to find the half equivalence point, you just look, you'd follow the straight bit, straight down to get the equivalence point, a volume added. It's 50, half it, you get 25. You go straight up till you hit the line, go along, and you'd find the pKa, which is the pH at half equivalence point. It's when half the acid is neutralized, and then the concentration of the acid will equal the concentration of the salt. If you have that, if you put it into our equation here, you're going to have the concentration of the acid equaling the concentration of the salt, so it's going to be the minus log 10 of 1, and therefore the pH is just going to equal pKa. How does the shape of the pH curve change as the acid strength changes? You can see there that a strong acid is going to be obviously far lower down, and you can see that it stays flat here. And the weaker the acid gets, you start to get this kind of shoulder thing going on. Even greater one. And then we've got a really weak acid here. You've got this leap up, then it flattens out. Okay? And you can see the angle of the equivalence point section is more angled here, where it's very straight for the strong acid. Okay, strong acids and weak base titration curve. You can see initially the pH suggests a strong acid. It's starting just above 0. The pH is below 7 at the equivalence point. Let's just find where the line is, halfway between that and that. Go along and you see it's below 7. You've got a final pH between 9 and 10, so it's a weak base. And you can see the volume of the base needed to reach the equivalent point was 25. An example of this reaction could be hydrochloric acid, strong acid, and a weak base, ammonia, to give ammonium chloride. And obviously, we're going to get an acidic salt. It's acidic because you've got this strong acid and you've got this weak base. Weak acid and weak bases, you can see here, initially, you've got a weak acid starting at about 3. You've got a bit of the shoulder going on. Then you've got, it's a bit of an angle. It's more difficult to really work out exactly where the equivalence point is, but it is still halfway between the two lines, the flat sections, or the not so flat sections. The final pH here suggests a weak base. Again, just follow this straight down for the volume of base needed to reach the equivalence point. It's just 25 in this case. And if you follow halfway between these and these, the equivalence point is taken straight along. You can see the pH is at 7, but roughly 7. It would depend on the relative strengths of the weak acid and weak base. In this case, an example could be ethanoic acid and ammonia. And obviously, the weak acid, weak base, we're going to get a neutral salt. And like I said, it does depend slightly on their relative strengths. Other titration curves, if you're adding the acid to the base, they're going to just go the other way. Strong acid, strong base starts at the top because it's a strong base in the analyte. As you add the acid, pH drops. You get this long straight line here, and you can see it's leveling off at a very low pH, so strong base, strong acid. Here you've got the weak base to start with, and then you're getting strong acid. You see it's coming at the very bottom. This time you've got the strong base, but it's going barely below 7 here, so you have the weak acid, and you've got this really kind of weak line here, and where you've got the weak acid and weak base. Ideally, an indicator should change colour at the equivalence point of the titration. Can you suggest a suitable indicator for this titration? So you can have a look in your data booklet at the indicators and which one would be good here. What you want is for the pK, the indicator, to equal the equivalence point of the pH. That's the ideal solution. So in this case, bromothymol blue has a pK of 7.3, which is very close to the equivalent point, pH of 7. The endpoint may be more difficult to recognise when there's an intermediate colour between the acid and base colours. Sometimes other indicators are used where the pK doesn't quite equal the equivalence pH. Suggest a reason why these are also suitable. So have a look at this graph. Why, even though thymol blue pK is evidently above the equivalence point, as is methyl's red, why are they still suitable? Well, their entire transition pH range falls on the steep vertical section. So they will go through the total colour change in the steep section. The volume required to reach the end point, the colour change, is the same as the volume required to reach the equivalence point. It's still, in this case, 50 ml. Why do we usually use phenolphthalein for strong acid and strong base titration? Why do you think? Well, that's because phenolphthalein is similar to thermal blue. It's got a pH range of 8.2 to 10. The pH change of the titration jumps from 4 to 10 within a negligible volume, even though the pH of the end point is higher than the equivalence point. It occurs at the same volume of titrant added. Let's consider this example. What type of titration is shown? Well, obviously it is a weak acid. We're adding a, what does that go to? It goes to 13, a strong base. And we have an intermediate acidic pH start. That's one of the reasons we know. High pH at the end, another reason we know. Our equivalent point is above 7, so we know a basic salt's going to form. And we've got a kind of shoulder region indicating the formation of a buffer. So there's several reasons why we came to our conclusion. Which indicator are suitable and why? Well, phenolphthalein would just be perfect because it falls right in there, and you can see its pK is right on the equivalence point. And we're just wonderful to use. Which indicator is not suitable? Well, the methyl orange there is well below the pH range of that steep line. It would be absolutely no use. It would not change it. It wouldn't change colour. Oh, sorry, it would change colour, wouldn't it? The colour change would happen before the equivalence point. The colour change is going to happen just really early on, before the equivalence point. Litmus would be no good because transition pH range occurs over a large volume, 10 to 25 milliliters, starting well before the equivalence point. So you see, it would start changing colour about here, wouldn't it? Yeah, well before the start of this steep section. Let's consider this example. What type of titration is shown? Give reasons. Well, we can see it's a weak base titrated with a weak acid because you've got the pH starting at a weak base and leveling off at a weak acid. And there's no definite steep vertical change. Which indicators are suitable for this one and why? Well, bromothionyl blue would be suitable because transition pH range is 6 to 7.6, occurs near the equivalence point and over a very narrow volume. It's as good as we're going to get for this one. You can see here the phenolphthalein would be no good. Transition pH range 8.5 to 10 is above the equivalence point, pH 7. And the colour change happens before the equivalence point. And methyl orange, no colour change would occur at all. It's after the zero crossover. Strong acid and strong base titrations. Some titration calculations. If you've got a battery acid sample from a car battery with H2SO4 being titrated with 0.7453 molar sodium hydroxide, the following data is collected. Got 10 centimeter cubed of battery acid. The initial vol NaOH is 1.25. Final vol NaOH 39.75. We've got to calculate the concentration of sulfuric acid. So it'll be a few steps. Step 1, we'll determine the amount in moles of sodium hydroxide required to reach the equivalence point. First of all, how much volume did we use? It's just, we start there, end there, so we use 38.50, take away one from the other. We've got the volume, so we now need to know the concentration. So CV, concentration multiplied by volume, will give us the amount of moles. There's the reaction that we're looking at. So next step, we'll determine the number of moles of sulfuric acid in the sample, and you can see it is 1 to 2. So we'd use this as a conversion factor to go from the moles of NaOH to moles of H2SO4. And if we want moles of H2SO4, it will go on top of our conversion factor to get the moles of H2SO4. Then we can determine the concentration in moles per decimeter cubed of sulfuric acid by dividing by the volume that we had. And we end up with 1.434 moles per decimeter cubed. Titration calculations. Again, this time with the weak acid, strong base titrations. A frequently asked question. Are they different from strong acid and strong base titrations? Does it matter that weak acids only partially dissociate? And the response is a big fat no. You've got to treat all acid-base titrations the same way. In other words, there is a complete reaction between the acid, strong or weak, and the base. A common mistake is to think that since weak acids partially dissociate and have a lower hydrogen ion concentration, less base is needed to neutralize the acid. But no, you can see all those zeros on the no. They're not zeros, they're the letter O. Let's think about Le Chatelier's principle. You've got ethanoic acid or weak acid in equilibrium with the hydrogen ion and the ethanoate ion. When you add sodium hydroxide, the concentration of the hydrogen ion decreases. The equilibrium will shift to the right, and more ethanoic acid will dissociate. As more hydrogen ions are neutralized, then more of this dissociates. Eventually, all of the ethanoic acid will dissociate as this gets mopped up. Example 2. Sample of vinegar from a fast food outlet is analysed with sodium hydroxide to find the concentration. We've got 20 centimetre cubed of vinegar. We've got a concentration of 0.425 of sodium hydroxide. Initial volume of sodium hydroxide is 1.25. Final volume 39.75. We're going to calculate the concentration of the ethanoic acid. We've got this reaction here written out. Weak acid, weak acid, strong base. So the volume of sodium hydroxide added is going to be final volume minus initial volume, gives that volume there. Then we're going to do, to get the moles of sodium hydroxide, we're going to do concentration times the volume. Obviously we're going to change centimetre cubed to decimetre cubed first. Now we've got the moles of sodium hydroxide. There's a little reminder in yellow, just because so many people get a bit confused with that. Determine the number of moles of ethanoic acid in the sample next. Well, let's go back there. We can see it's 1 to 1. So our conversion factor to go from moles of sodium hydroxide to ethanoic acid, we'd have to have our conversion factor would have the molar ratio with ethanoic acid on the top, and so we're going to get 0.01636 moles of ethanoic acid. Now we can determine the concentration because we know the volume. Divide the moles by the volume to give us the concentration. And that's the end of that presentation. Splendid.